guys, I just wanted to go over a couple of the questions I was going to assign for you. I've got 5 of the 8 I want to go over, so you can get a lot of help with your homework if you want. So just 5 ones that are a bit different. First guy, not very hard. You're just basically plugging it into the formula. However, you got to use your standard units, your SI standard units, which is coulombs and meters. So we got to convert these. Remember, micro means 10 to the 6 or 1/1,000,000th of a coulomb, and centimeters is 1/100th. So it's fairly simple. Again, I'm not going to fully do the solution for you. I'm just going to write out how you figure it out. So your electric potential, your voltage, is equal to your 9 times 10 to the 9. Maybe I'll just write that down. 9E9 times the charge of the thing causing the electric potential, which is 2.5 times 10 to the -6 for micro, and then all over 0.06 to convert centimeters to meters. And that's it for that guy. That is all she wrote. So for this guy, I want to do it just because it mentions work. And so I wanted to do a reminder that work equals change in energy. So that's what we're going to do. We're going to say, hey, work equals change in energy. And in this case, the change in energy, it's always final minus initial. So let's just say it's we'll do EP final minus EP initial. So we will go and do our K. I'll just write it as K for this one. 9 times 10 to the 9. Charge of the first object, 5 times 10 to the -6 times the charge of the other object, 0.03 times 10 to the -6, all over their final distance, which it has to be in meters as well, so 0.15, and then we will subtract the exact same thing. If you're smart, you might be able to figure out how to combine them. So you don't have to plug it in your calculator twice. 10 to the -6 coulombs, so the charge of the both things, and then we will divide it by the initial distance, which was 0.45 meters. And that's it. Work equals change in energy. There you go. Final potential energy minus initial potential energy. All right, for this guy, I just wanted to bring you back to your energy before equals after. So we'll do before equals after. By the way, anytime you've got speed or anything like that, odds are you're doing something like before equals after, or kind of if your potential energy goes down by, I don't know, 300 joules, your kinetic energy will go up by 300 joules. So you can kind of use a formula like your negative change in potential energy equals your kinetic energy, but pretty much any question you can solve like this, you can also solve with before equals after. And so that's what we're going to do. So initially, it's super close to this charged sphere. Remember, we're going to have to use elementary charge for the proton, so we'll just do our KQQ over R before for our potential energy. So K, charge of our proton, which is 1.6 times 10 to the -19, elementary charge in your data pages. Charge of the fixed sphere, which is 6.4 times 10 to the -18, which notice is sort of a multiple of this guy, or should be. And then we will divide it by the initial distance, which is 2 times 10 to the -11, which is very small, so this will actually be a fairly big potential energy, even though or relatively so, even though the charge is so small. And then initially it's got no kinetic energy. So we'll leave that there. We just had potential energy before. After, we're 0.5 meters from the center, which we can totally put in. I'll write it down just for fun. But I'll tell you why it's essentially useless after. All over 0.5. All right, and then we'll just add our kinetic energy term, which will be 1/2 m, which is 1.67 times 10 to the negative 27 for a proton, and then v squared, and we're going to be solving for v squared. But the reason why this is essentially useless is because it is so much smaller than this guy, or it is this distance is so much bigger. It's like 10 to the 10 times as big as this guy. So this force is like 10 to the 10th power, or not force, this energy is like 10 to the 10th power times as small as this guy. So close enough to zero we can ignore it. The amount this affects the situation is way less than our error in significant figures. If this was 6.41 instead of 6.4 secretly, or 6.401, it would still be like 9 or 10 to the 9 times as potent, or 10 to the 8 times as more important than this whole term. So since the effect is so much smaller, we can ignore it. Anyway, so just solve for v at this point, and you totally don't even have to write this because it's so much less energy than this initial. All right, next guy I want to go over. This guy's tricky. It's just kq over r plus kq over r plus kq over r with your 3 distances. So make sure you're using the distance of 7.5 for this guy, 17.5 for this guy, and 27.5 for this guy. But I figure we get most of the idea going on with this one, plus the fact that arrangement doesn't matter. So if we want to find the potential at point P, we just basically got to do kq over r for our 3 charges with the distances away. So one of the first things we should do is maybe figure out what this distance is. Fortunately, we've got a right triangle with sides 6 and 8. 6 squared is 36, and 8 squared is 64. 36 plus 64 is 100. Square root of 100 is 10. So this is one of your special triangles that works really nicely with Pythagoras. Anyway, so if we want to find our total voltage at this point, our total electric potential, it's just K times 1 times 10 to the minus 6. This is our Q1 term. We'll call it V1 plus V2 plus V3. V1 being the electric potential due to Q1, V2 being the electric potential due to Q2, and V3 being the electric potential due to Q3. So you've got K times 1 microcoulomb over the distance is 8. 8 centimeters, so we got to do 0.08 plus K times -3 times 10 to the minus 6 all over our distance of 10 centimeters, so 0.1 meters. And then same thing for V3 with 6. So K times 4 times 10 to the minus 6 all over 0.06. And that's it. That's all you got to do. It's pretty nice working with these scalars just because you don't care about the arrangement. All you care about is distances. And you just plug stuff straight in your formula. Now, number 7 I want to go over, just because a key idea with all this stuff is potential energy is a property of a system, whereas kinetic energy is a property of a specific object. So you've got, for these 2 alpha particles, we have 1 potential energy for both, for the system, and we have 2 kinetic energies, which relate to the speed of each, at least in a particular reference frame. All right, so we'll do just a before equals after because we're finding speed, and that's pretty much always what we do. When we got speed, before we got potential energy only. So we have K times the charge of an alpha particle, which is 2 times the elementary charge, so 3.2 times 10 to the negative 19 squared, because there's 2 of them. So it would be this times the same thing. And they are start off 2.5 times 10 to the minus 12. Notice again, we've got an astronomical difference between the potential energy before, because this term is so small, and afterwards they're 0.75 meters apart. So the difference in energies is off by a factor of like 10 to the 11. Or something ridiculous, so we're not even going to bother writing it. And so, but afterwards, they each have a kinetic energy. It'll be split between them, since they're equal objects, same charge, same mass. Now, their mass is roughly 4 times the mass of a proton. 7 times 10 to the negative 27, so that's your total mass, 1/2 m, and then v squared. And then we'll solve for that. That's it. 2 because we have 2 alpha particles and they each have a velocity, but they only have 1 potential energy between them. So potential energy, property of the system, kinetic energy, something possessed by each object in a particular reference frame. All right, a bit of a long haul, but hopefully that helps a little. Thanks for listening.